Once we've worked with absolute value equations, absolute value inequalities, it seems reasonable to come next. Frequently, we'll solve a related equation when we do these. Not always, but sometimes. So if we have an absolute value graph and it's equal to a y value of k, we worked on finding the solutions S1 and S2. Where is this value equal? Just like the speed limit example from the end of absolute value equation video. But now we're going to look at when we don't have equality. We have a less than or we have a greater than, and this is a great representation of what it'll look like graphically. This was taken from Roxwold's College Algebra with Modeling and Visualization, the 6th edition. So thank you, Roxwold Pearson. I stole that, but I credited it, so I hope that's all right. All right, so in order to work with inequalities, let's use the definition of the equation. Let the solutions to absolute value of ax plus b equal k be S1 and S2, so solution 1 and solution 2. And just to have order, solution 1 is less than solution 2. We could order our answers whichever values we get. And k has to be positive. It cannot be 0. It has to be positive. The absolute value of ax plus b is less than k is equivalent to S1 less than x less than S2. And absolute value of ax plus b greater than k is equivalent to x is less than S1 or x is greater than S2. And this is showing here that the absolute value, the blue portion of the graph, is less than k, below the line of k, between the values, so x is between, whereas the absolute value is greater than k, it's higher than the k, outside of the solutions. All right, and so that's exactly what the property is telling us. Similar statements can be made for the greater than or equal to, less than or equal to. So we're going to solve the absolute value equation, and then we're going to solve the related inequality. We might even check this graphically. We'll see. I encourage you to check it graphically if I don't. So to solve the equation, we have the absolute value of 6 minus 3x equals 3, which leads us to 6 minus 3x equals plus or minus 3. So we'll have 6 minus 3x equals 3. We can subtract 6 from both sides. Minus 3x equals minus 3. X equals 1 if we divide both sides by a negative 3. But we also have 6 minus 3x equals negative 3. If we subtract 6 from both sides, minus 3x equals minus 9. Divide by negative 3, and we'll get x equals 3. So we have our S1, and we have our S2. And the order of them is just because 1 is less than 3, then this is S1 and this is S3. If we had a different situation, perhaps it was 3x minus 6, maybe the S1 and S2 would be switched, and that's okay. Now we want to look at greater than 3. If we're looking at greater than 3, the absolute value inequality with greater than tells us our solution will be outside of the values. So my answer will be x is less than 1 or x is greater than 3. In inequality notation, right, we take this number line, 1, 3, x is greater than 3, x is less than 1. We can write this in interval notation as negative infinity to 1 or 3 to infinity. So an x value in either of those two intervals will make this inequality true. And I encourage you to check it by graphing. I'm going to skip that for right now, although I will show you on a graphing calculator, on the TI graphing calculator that I use. When you go to y equals in order to graph it, if you go to math, arrow over to number, here's the absolute value. Yours may or may not show the absolute value lines. It might just show ABS, and that's all right. And since I'm already here, we're just probably going to graph this. 6x minus 3x, compare it to 3. Let's graph. And you can find the intersections to make sure, but the answers are 1, vertex, not vertex, this is the pointy spot, the cusp. corner, and 3. Fantastic. Yes, the absolute value is higher than the k value of 3 whenever we are outside the intervals. So we're able to check it graphically as well. So let's solve some absolute value inequalities. In order to do this, we always start with 3x minus 1 equals 8 in absolute values. We'll solve the related equalities. Always a positive one, always a negative one. When we add 1 to both sides here in green, add 1, we'll get 3x equals negative 7. So x equals negative 7/3. And in blue, when we add 1, we'll get 3x equals 9. And when we divide by 3, we get x equals 3. Because this is a less than tells us we are between the two values. Notice negative 7/3 is smaller. So my answer, negative 7/3 is less than x is less than 3, which we can rewrite in interval notation as negative 7/3 to 3, using parentheses because it's a strictly less than example. If we have less than or equal to, oh, I didn't realize I used less than for both of them. That's all right. 7 minus 4x, solve the related equation. So 7 minus 4x equals 11. Let's subtract 7 from both sides. Negative 4x equals 4. So x equals negative 1. Also solve the negative 1. When I subtract 7, I'll get negative 4x equals negative 18. When I divide by negative 4, negative 18 over negative 4, both are negative, so we get positive as a result. 18 over 4 is the same as 9/2. Yes, you could use 4.5, but I encourage you to get familiar with fractions. Get used to them. Less than or equal to, so we're between. Notice the negative 1 is smaller. So negative 1 is less than x is less than 9/2, or the interval from negative 1 to 9/2. All right, so solving the related equations helps us solve the inequalities. Less than is between, whereas greater than is on the outsides. But there's an alternate method. The alternate method of solving absolute value inequalities, if k is a positive number, instead of saying it's between, we could just solve this whole equation. We don't solve the related equation first. We could just go straight to the inequality. So let's use a different color here. I keep going back and forth to blue and green. So let's use this light blue. Because we're at less than, we can solve negative 20 is less than 5x minus 7.5, which is less than positive 20. When we add 7.5, we add it to every single area. So it's not both sides, it's all three portions, anything that's separated by an inequality symbol. A negative 20 plus 7.5 is going to be a negative 12.5. In the middle, we'll have a 5x and 27.5. Our next step, we're going to divide everything through by 5. Our goal is to isolate the x in the middle. So let's bring up a calculator. And negative 12.5 divided by 5, negative 2.5. I probably knew that. And 27.5 divided by 5. Probably another one that I should know. But as I said earlier, when you're recording, your mind goes out the window. And we have our answer already. We didn't have to solve something else and then remember a property. We could go straight from a property into the solution. This is negative 2.5 to 5.5 in interval form. One more basic example. Let's go in purple. If 2x minus 3 is greater than 1, using our alternate phrasing, we know that 2x minus 3 is less than negative 1 or 2x minus 3 is greater than 1. So if you have a greater than, one of them stays the same. Right? The one on the right always looks the same. Absolute value of 5x minus 7.5 is less than 20. You can see that here. But the negative 20 goes on the left because it's between. Here, we have to change this inequality a bit. We have to change the sign so it gets flipped around. When we add 3 to both sides, 2x is less than 2. Divide by a positive 2, and I'll get x is less than 1. When you subtract 3 on this side, we get 2x is greater than negative 2. When we divide by a positive 2, we'll get an x is greater than negative 1. And if you ever get an answer that you're unsure of, don't be afraid to check it. So we have the absolute value of 2x minus 3. And we want to compare that to 1. Okay, those values are not correct. Oh, indeed. The 1 is correct. Always. See, that didn't set right with me. X is bigger than negative 1 didn't set right. And the reason for it is because of this step. Sorry. This is the step I screwed up on. What did I do? I didn't write down my work. 2x minus 3 is greater than 1. When I add 3, that gives me a 2x is greater than 4. Greater than 4. When I divide, I get x is greater than 2. And that looks more reasonable. All right, the 2 is reasonable, the 1, and it looks like the pointy spot is right in between. So always, this is a caution here, write steps to avoid mistakes. I did not do that on purpose. I never make mistakes on purpose. I do enough of them on accident that I don't need to. All right, so this is my bad. This is why we always write our steps. If you caught that before I did, good job. All right, so an aluminum can should have a diameter of 3 inches with a maximum error tolerance that is less than 0.004 inch or 4 thousandths of an inch. Write an absolute value statement that describes the situation. The diameter needs to be super close to 3. How close to 3? Within 0.004 of 3. All right, within, so less than or equal to. We can equal that much because it simply says less than. We're not going to question that. Not going to question the English. So this is part A. All right, the diameter needs to be close to 3. How close to 3? This close to 3. In order to solve it, since it's a less than, negative 0.004 less than d minus 3, which is less than 0.004. When I add 3 to all 3 positions, I will get 2.996 is less than d, which is less than 3.004. This means that the diameter of the can may be anywhere from 2.996 inches to 3.004 inches. So there's a little bit of variance in the cans, but not that much. That's why they almost always stack nicely. All right, that is it for absolute value inequalities. Thank you for listening.